All right, howdy, Ags. We're back for part 2 of mechanical analysis, at least some background information. So let's start talking about kinematics and kinetics. Kinematics and kinetics, what the heck are those? Well, they come from kine. That's a verb that means to move. And kinematics is a descriptive analysis of motion, whether we're playing tennis, golf, shooting a basketball, spiking a volleyball, running, whatever we happen to be doing. And if we can film it with a camera and observe it, we can do kinematics. So what is kinematics? Again, it's a descriptive analysis of the mechanical components of movement without necessarily talking about the forces that cause the motion. To be honest, as recovering engineer, it's hard for me to do that. In fact, we probably won't do that at all. So we're going to talk about cause and effect the entire time here. But kinematics usually refers to me, it's the type of tools or the type of technology that's used to do it. Here we're talking about digital video cameras. We're talking about computers. We're talking about still cameras. We're talking about goniometers. We're talking about accelerometers. Anything that can measure distance, displacement, velocity, acceleration, whether it's linear or angular. You're going to get a chance to do all of those. So we may follow, for example, the path of someone's arm and wrist as they're shooting a basketball free throw. We could be following the angular velocity of a joint. So kinetics goes along with kinematics. To me, it's hard to separate them. The tools are a little different. Kinetics is the causal analysis. What causes the changes in motion that we see during kinematics? So we're dealing with force, momentum, impulse, the ability to change momentum, torque, momentum. I mentioned momentum. It's so much. Impulse, power, work, etc. So we could be, let's say, analyzing how much force and pressure there is between the foot and the ground with a force plate or pressure plate when someone's jumping, maybe doing a high jump. We can use the pressure plate to see if the training they're doing is enhancing their performance. Or we may be able to determine whether or not some shoe wear that we designed or we're trying is helping a diabetic patient who may have sores and problems with their feet. This can be a real issue for diabetic patients because the healing process is a lot slower. And so, and that's largely because our ability to produce microvasculature, capillaries, arterioles, etc., that feed the injured tissue is impaired. So that's why the healing process is a lot slower. It also affects protein synthesis as well. So those two reasons are the main problems with people who have severe diabetes, whether it's type 1 or type 2 diabetes, and especially when they're insulin-related problems. Stress on a knee joint during a squat exercise, that can be high indeed. So we have a fairly large concern about that. And as I mentioned, kinematics and kinetics, to me, as someone who's interested in measurement, and hopefully you guys are, and testing, has to do with the tools that we can use. So kinematic tools are your senses themselves, photocells, film analysis, digital video, cameras, goniometers, accelerometers, anything you can use to measure distance, velocity, acceleration, anthropometric measures, etc. Kinetic tools help to measure force, pressure, tension, power. So we have force plates and pressure plates, tensiometers, which measure tension, pulling forces. We have a wind tunnel at Texas A&M, which we can use to look at fluid drag. Dynamometer is another way to measure force. Cybex and Biodex machines measure joint torque. Treadmills and cyclergometers are used quite often. Electromyography, EMG, is used to measure electrical activity that muscles are producing. And of course, if we can interface them with computers, all the better. So if you remember this slide from our first session, this is the kind of stuff we actually have here in our laboratory. We have a Tendodyne system to measure power. We have high-speed video cameras. We've got regular old video cameras as well. We've got a Biodex machine, a MAT scan, pressure and force plate. We can do anything that I think you want to do. And some of this is portable, so if you can't film it in our laboratory area, or you don't use some of the filmets in our laboratory area, you can go elsewhere to do that and socially distance while you do it. So, well, measurement and testing is what it's all about. So there's some factors to keep in mind when you're making measurements. Is the measurement precise? How exact is that number? The good news is the equipment that we have is extremely precise. That's good. Is it accurate? Well, you have to test that out. How correct is the number? If I'm driving down the street and let's say that my speedometer says I'm going 50 miles an hour, but I'm really going 60 miles an hour, or that's what the policeman tells me when they pull me over, then I am in trouble. My measurement is not accurate. I can say in court that, hey, the police's radar gun wasn't accurate, but that often doesn't work. Accuracy is incredibly important in terms of measurement. We want to make sure that the data, the number we get is right. Another factor that's virtually as important is reliability. And that means reproducibility. When you make a measurement with a given system, let's say you're measuring torque under the same conditions with the same person, you should get pretty much the same number. Is it reliable when you turn the key on your car or truck? Lately, because we haven't gone out as much, it's been a few days since we turned on that car or truck. Maybe it doesn't want to start. Maybe the lawnmower doesn't want to start either. So is it reliable? That means if we repeat a test or a measurement, we get, under the same conditions, we get a similar or the same type of result. Is it valid? Is it applicable? Is it have meaning? Is it appropriate? Does it measure what we're supposed to measure? So you don't want to measure your weight with, obviously, a meter stick. Okay, so this starts to lead us into some basic variables that we'll be using throughout the semester. And they are things like position, time, and mass. Everything else that we're going to discuss, from velocity, linear and angular acceleration, force, pressure, momentum, impulse, torque, angular momentum, work, and energy, and I mentioned power, mechanical stress and mechanical strain, are all going to be derived from these variables. And in your physics and your calculus classes, hopefully you notice the connection between them. That's what Isaac Newton was about in terms of developing differentiation and integrals, is to go up and down that variable pathway from distance, velocity, acceleration, force, torque, impulse, momentum, etc. So we'll start with position, location. You got to know where you are first. That's why those reference systems are so important. That's why we covered them first. Those are basically the rules in terms of measurement. Now we start with position, and because movement occurs in time and space, we're going to look at a series of pictures, motion pictures, if you will, as people and objects move. So we first have to start with location or position. And the position of an object is its location in space relative, to some baseline value or axis. That's basically your reference. If we think about each of the reference systems, each one has an origin. That's our reference point. So linear position and Cartesian orthogonal coordinates, standard units are going to be critical for us. If you know your standard units, you can actually remember the basic equations for things like velocity and acceleration and force and torque, etc. So in the English system for position and distance, it's feet. And in the metric system, it's meters for whole body biomechanics. So keep those in mind as we move throughout our variables. So position, if it's angular position, that's an arc. And here we mean rotary or angular coordinates. The standard units are actually radians. They are radians. Okay, hold on a second. Pause. Okay, so remember, radians are the standard units for angular position and arc. So here we see an Astro's picture, incredible amount of, that is lateral rotation or external rotation of the shoulder. Oh my gosh, it hurts just to look at it. But think about what a kind of whiplash action you get, because you're going to get incredible amount of internal or medial rotation during the throw, combined with horizontal adduction of the shoulder. You're really taking that spring, winding it up, and just letting it go. And that's how you can get a 95 to 100 plus mile an hour fastball. You have to do a lot of flexibility exercises. Okay, the next variable is time. Time's a measurement from one moment to another. The standard units for time are seconds in the metric in the English system. Doesn't really matter. Mass is a quantity of matter composing an object or a body. So on Earth versus the moon versus space flight, let's say I managed to become an astronaut somehow, and if I was blasted off into space under weightless conditions, I would have the same mass, at least for a while, until I lose muscle mass. On the moon, I'd have the same mass. On Mars, I'd have the same mass, hopefully. Weight would be different because that's the force of gravity acting on that mass. Now, the standard units are interesting. People get confused by them. In the metric system, it's actually kilograms. Kilograms are not units of weight. They're units of mass. I know your doctor scale says pounds and kilograms. It's a little confusing. In the English system, it's slugs. People forget about those standard units as well. But that's critical, because when we get up to force, we're going to take units of mass and then multiply them by units of acceleration. One slug in terms of conversion factor is 14.59 kilograms. The main conversion factor you're going to have to be concerned about is degrees to radians. This one, don't worry about it. Okay, so with motion analysis, we're going to basically go from distance to velocity to acceleration to force as we differentiate. And out in the calculus, we're moving up the line here. Inertia, then we'll talk about torque, momentum, impulse. That's the ability to change momentum, work and energy, power, mechanical stress and strain. So these are the main variables that are going to concern us throughout the semester. In fact, this is a reminder that all of these variables can be derived from position, mass, and time. So in a sense, everything else we're going to do is derived and applied from those three basic concepts of time, mass, and position. So one thing to remember, center of mass or center of gravity is a balance point, if you will. It's the average position where half the mass is to the left and half the mass is to the right. The golf clubs they have today, this is really interesting. This center of mass or center of gravity is actually fairly far from the head. Back in the day, oh my gosh, this persimmon wood balance point is actually considerably closer to the head. And let's see, I've got a metal wood. There's a steel wood back in the day. And this balance point was about right there as well. So the balance point was actually closer to the head and therefore farther away from the axis of rotation, the wooden club and the steel club actually weighed a lot more than a club today with a graphite shaft and a titanium alloy shell, and then there's foam in the center, which is a really light material. So in baseball, they talk about corked bats. This is basically a corked golf club. And that increases its elasticity and allows us to be able to swing faster. And we're going to talk about moment of inertia in a moment, and that's the resistance against angular motion. Plain old inertia is resistance against linear motion. And when we talk about angular motion, moment of inertia is actually the resistance against that. So we draw a center of gravity or center of mass as a point mass. Half the mass is to the left, half the mass is to the right. This can be 1, 2, or 3 dimensions. With a golf club, we're going to just assume it's in 1 dimension. Okay, so here is a sea change in mechanics for the high jump. People used to use something called a straddle technique. I tried that. It doesn't work too well for me. I've got a low center of gravity, low center of mass. I've got too much mass. I've got short legs. Really all the ingredients for disaster in terms of the high jump. So the straddle technique actually had you facing towards the bar and trying to somehow clear both legs, one leg at a time. It was crazy. So this is Dick Fosbury. He invented the so-called Fosbury Flop. The idea was that when you take off, you're going to try to raise your center of gravity as high as you can by raising your arms in one of the legs. And then when you go over the bar, you see hyperextension of the hip, flexion of the knee, and it's done so the center of gravity is at bar level, sometimes even below. That means I have to raise my center of gravity a shorter distance. That means less impulse, less force. And so the result is you can gain 2, 3, 4 inches. And obviously in international competition, that's everything. A few inches is the difference between no medal and the gold medal. So there's Dick Fosbury with a Fosbury Flop. So we can alter the center of gravity in our body by raising, moving the arms, moving the legs, changing its position. We can also think about the fact that center of gravity is not just along one axis. It can be along multiple axes and multiple planes. So for example, if you think about a donut or a wheel, most of the mass is away from the middle, which is the center of gravity. So this momentum, or I'm sorry, this mass is distributed far away from this axis of rotation. In fact, I'm just going to call this an axis right here. The axis of rotation, and most of the mass is actually right around, let's see what I can do here. Editing as I go with fun. There we go, there's mass. I'm gonna turn this into Arial font. Throw that right in there. So if you think about, again, kind of a donut or a wheel, or another example would be a long bone. If we basically cut this long bone in half and look down the barrel of the bone, most of the mass would be distributed far away from the middle. We'll call that the axis of rotation for the bone. So in 2 dimensions, if we can move the mass farther away from the axis of rotation, that actually increases the resistance against bending forces, torsion, as well as even shear forces, but especially bending forces. It works really, really well. So we say that as we increase the mass of a bone and move that mass farther away from the middle of the axis of rotation, that actually increases the moment of inertia. That's the resistance against bending forces as well as torsion or turning. We can think of it as torque as well if there's actual rotation. So golf clubs and tennis rackets really went through the same evolution over the last, well, about 45 years. And that evolution is twofold: increasing the distance between an axis of rotation along, we're going to call this the z-axis if we're hitting a forehand shot, the axis of moving the mass away from the axis of rotation along the z-axis. But one of the things about the sweet spot and moment of inertia is that it's dependent on the axis. So along this z-axis, we have mass distributed a long way away from it as we've increased the head. And that means that if we hit the ball off center, it's harder to turn because there's more resistance against torque and turning. The same thing is actually true for a golf club. As we've gone from a head that's, oh, here we go, really small like that, oh my gosh, to this size. Look at the difference. As we move the mass away from the middle, that increases what we call the moment of inertia. The moment of inertia is actually the product of the mass times some constant based on the shape times something called the radius of gyration. And that's roughly the distance between this axis to where the center of mass is in 2 or 3 dimensions. So when a ball hits off center on the big club, it has this much larger sweet spot. It's probably going to go straighter because even if it's off center, it's not going to cause a lot of torque. Torque's produced by off center motion. So if we move mass away from the axis of rotation, we can make that club more stable when it hits the ball. So we have cavity backed irons that do the same thing, that move the mass away from that axis of rotation. For a golf club, I would guess that this axis is going to be technically the x-axis as we're hitting our shot. Let me think about that a second. Yeah, our x-axis. Here's a tennis racket, and here's the difference between a wooden racket people might have used in the 1970s versus the type of racket we've used for the last 15 years or so, with these really large heads. And if we think about the swing axis, let's say if I'm hitting a forehand shot, my tennis racket is going out in front like that. So if we hit it off center, that tennis racket's going to try to rotate around the z-axis. And if we move that mass by having a larger head away from the axis of rotation, that increases along the z-axis this radius of gyration. And that increases the moment of inertia, therefore the sweet spot, and decreases the chance of an off-center shot twisting the racket in your hand. So the chances are you're going to hit a straighter and better shot along the z-axis. Now, here's where I think something cool comes in. When you're hitting that shot, you also have rotation around a vertical axis, a y-axis. So what happens there is that the total mass of this racket is actually much lower than a wooden racket or a steel racket. Also, its balance point is a bit closer to the handle. And that means that both, along the z-axis, both the mass and the radius of gyration are decreased. So that means the moment of inertia along the y-axis is actually down. When with the same racket, even though the mass is less, what mass you have around the racket head is distributed farther away from that z-axis. So in this case, R is increased. And remember, this moment of inertia is proportional to the square of the radius of gyration. That's critical. That means that this term goes way up. And if you hit it off center, like anywhere in this W, that's your sweet spot, you're okay. If you hit it off center, and really the sweet spot was about the size of a silver dollar, or the basically bottom of a Coke or 7-Up can. If you hit it anywhere away from that sweet spot, that thing vibrated in your hand and hit it to the left or right or who knows where. who knows where it went. It was really tough to hit with a wooden tennis racket. I wouldn't try to do that now. Couldn't hit it very fast either because it was heavy. And because it was heavy and had more mass, and the center of mass was distributed a little farther away from the handle, that meant you had this large moment of inertia that slowed down the movement as you're producing torque. So any torque that you're producing is trying to overcome the moment of inertia. The moment of inertia is larger. That means the angular acceleration is going to be slower. So the racket doesn't go nearly as fast. So I had a really bright idea, or at least I thought I did back in the day. Hold on a second. Before I thought about applying biomechanics, I'd had biomechanics as an engineer, but it really wasn't geared towards sports and a lot of applications that we think of today. It's come a long way. There's Trixie. Trixie's going to help us out with this. This is called a bomb bat. I was like, ooh, this is going to hit it a long way. I thought this was a really, really good idea. In fact, back in the day in the major leagues, when someone took out a big, heavy bat, they would say bringing out the heavy lumber, so you might be able to hit more home runs. It turns out that doesn't help you at all. The reason it doesn't help you at all is that this thing is really heavy, and the radius of gyration is pretty long. So that means the moment of inertia is high. That means I can produce a lot of torque, but the torque's trying to overcome this large moment of inertia. And we can break it down into a simple equation, believe it or not. Torque is equal to the moment of inertia times the angular acceleration. This equation looks a lot like Newton's second law for force. Force is equal to mass times acceleration. Mass is the resistance against force. Force is trying to change linear velocity. And the change in linear velocity is, of course, acceleration. So F equals ma. So in the case of torque, you have torque is equal to the moment of inertia, which is like mass, times the angular acceleration. So because the moment of inertia, this bomb bat, I thought I was going to hit a lot of home runs. When I was playing on my softball team, I hit 0. And I guess I can blame the bomb bat now, probably my technique as well. But this didn't help me, because we know today, if you're going to hit a golf ball a long way, or hit a tennis ball with a lot of velocity, the Williams sisters can hit it 130 miles an hour. There are some guys in Wimbledon and the U.S. Open that can hit it 140 plus. I think the records of maybe 150, 155 miles an hour. But they can hit it really super fast. And part of the reason they can do that is the design of this racket. It's lighter. So Barry Bonds hit a lot of home runs. He might have had some help along the way, but he probably would have broken 755 and Hank Aaron's record if he hadn't participated in the ergogenic aid and possibly HGH or whatever he might have taken back in the day to hit a lot of home runs. It actually probably caused him some joint and other problems that actually slowed him down at the end. But he was on pace to actually clear 755. Anyway, he just wouldn't have had a season where he hit 73 home runs or something like that. He might have gotten to 55 or 60 during his best year. But he was working at a Hank Aaron, a little higher than a Hank Aaron pace. At age 37, you usually don't go from Hank Aaron to Babe Ruth type pace in terms of hitting home runs. So little unusual, but nonetheless, what I'm getting to is that what Barry Bonds did right is he didn't take out the heavy lumber like Willie Stargell back in the 1970s for the Pittsburgh Pirates. Barry Bonds started off with the Pittsburgh Pirates. What he did is they used to use 43-ounce bats, really heavy, like his bomb bat. And unless you were Willie Stargell or someone with a lot of power, that could generate a lot of torque, you couldn't hit home runs. really heavy lumber. The bat went slow. We know now that clubhead speed, racket speed, bat speed is everything. So Barry Bonds figured this out and used light bats. He used like 32-ounce bats. So with low mass, and he used to choke up. So here is the leading home run hitter, with or without some extra help. He used a light bat. A bat with a mass I would have used in Little League. But that was the smart thing to do, because why? With a reduced mass and a reduced radius of gyration, that meant a low moment of inertia. That means for a given torque he could produce really fast angular acceleration. That means really super fast bat speed. And if you can get the bat speed up so you can hit a baseball over 100 miles an hour, you might be able to hit home runs. 115, 120, I think, is about the max we see. Sometimes with the center of mass and center of gravity, we want to keep it steady. So a classic example is, and we see Gail Devers here, is the hurdles. So with the hurdles, what we want to do is when we raise a leg or raise an arm, that would raise our center of gravity. When someone clears the hurdles, they don't really want to jump over them, because each time they do so, they would have to raise their mass and increase their upward momentum. That's going to take a lot of force and a lot of time. That's going to slow them down and exhaust them while they're trying to clear this 110-meter hurdle race. And I think they have 10, if I'm correct, 10 hurdles to clear. So what they do is notice when the leg goes up that the torso goes down. So that means as the torso goes down, it keeps that center of gravity from lifting. That means they can clear the hurdle and maintain their center of gravity or center of mass. That makes a big difference. So here we see that leg going up and then the torso going down. So I'm going to show you in a second here a classic example. It's from the Olympics. The film quality isn't so great anymore because it's from the 90s. But we're going to look how important it is to clear the hurdles. It's almost better to knock them down than to jump over them. So hang on a second.
In lane 6. Amelia Valle of Cuba, drawn in lane 7.
We're looking at the 1996 Olympics,
drawn in lane 8.
And we're going to have special attention to Alan Johnson in lane 6. And we're going to see him take off. We're going to see him literally clear those hurdles.
Away first time, Colin Jackson got very well, and so did Johnson.
See if I can catch it there. Ooh,
and the swat off.
There we go. You can barely see that, but see how that lead leg comes up and the torso goes down? He's going to clear the hurdle instead of jumping over. In fact, he's going to knock them down. They're balanced, so it just takes a little bit of force to push him over. And he's got 4 years to recover anyway. Just that hamstring probably hurts.
The Olympic record has gone. And what we suspected, well, it just happened.
New Olympic record. Pretty good. So you can knock down 9 out of 10 hurdles and still get the Olympic record.
Piece of sprint hurdling. Colin Jackson got away well, but between those hurdles,
show it again. Here we go.
It was very
slow motion. You see that lead leg come up, torso go down.
Johnson
right in face, perfect.
Away at this stage.
Boy, he's doing it really well. I think that's the key.
Swift coming through, Swartoff coming through.
Probably was about an inch or two closer to each hurdle than he wanted to be. But he used to smash that. There we go.
And I think Swartoff is confirmed in third. Yes, he is.
Okay, the last thing we're going to keep in mind is we go through kinematics and kinetics. So this second portion of mechanical analysis before we start to apply and do some problems with the center of gravity is our body segments, our arms, legs, upper arm, thigh, torso. All of them have a center of mass or center of gravity. These have been worked out with cadavers and real live humans. So we have a pretty good idea. Rule of thumb usually says the center of gravity for, let's say, the upper arm is a little closer to the shoulder than it is the elbow. Most people have a little bit more mass closer to the shoulder than they do the elbow. The same thing is true for the forearm. Got a little bit more mass closer to the elbow than I do the wrist. It's about 45% from the proximal end. So it's going to be about right here for the forearm and about right here for the upper arm. This is important because we can use this type of analysis with an axis of rotation and a center of mass to calculate things and figure out things like torque. How much torque is the upper arm and the forearm producing on the shoulder? And if I'm holding a weight, how much torque is that producing? So all of these things are going to be important when we're analyzing things, because torque is the key thing that we're going to have to produce to overcome moment of inertia, outside torques, antagonist muscles, etc. Excuse me, got little hiccups. So that's a signal to stop. And we're going to pick up with a very short review of trigonometry, and then we're going to get into applications relating to kinematics, distance and velocity, and then moving up towards acceleration. So have a great day. We will see you soon.